Okay, you can hear me in the back? Okay, so I want to start exactly where we left off at the end of last time, because we did it a little bit in a hurry and it's really important. So basically we finalized what we know about learning theory. I feel it's a little bit too loud, no? Is it? No, okay. So we talked about VC dimension. And really VC dimension is important not because you're going to compute it all the time except for in homeworks, but because it gives a lot of insight into when things are learnable, when they are not learnable, and even, or as important, to model selection. And in order to extend it, at least in one important scenario to understanding model selection, we need to be a little bit more subtle, and that has to do with a data-dependent notion of VC dimension. So when we talked about VC dimension, we defined it for a fixed class of functions. We said this class of function has this VC dimension. And we said basically that if it's finite, Occam razor says that you're going to be able to learn. But we also noticed that if you have a smaller VC dimension, learnability is going to be better in the sense that, you know, the gap between training error and true error is going to be smaller, right? This was the key generalization thing. So I want to give an intuition, and the intuition is going to be, again, in the context of linear separators. And this is the problem that we looked at. So we looked at a collection of, you know, blue points, positive examples, red points, negative examples, and two options for linear separators. And you all agreed that you prefer, which one you prefer here, H1 or H2? H2 is preferred. And the question is, why do you prefer H2, and how can the theory that we've covered so far actually can guide us and tell us, yeah, H2 is a better one. So here is what the theory says, right? The theory says, look at this gap between the true error, the one that you want to minimize because it tells you how well you're going to do in the future, this one here, and what you've seen in the training. And basically what we've shown is that the gap between these two depends on the VC dimension of the class of functions, and a few other things, you know, the delta, which is the confidence within which this is going to happen. But in this case, just taking the class of linear hyperplanes is not going to be subtle enough, because the example that I've given, the training error of both H1 and H2 was 0, right? They were consistent with the data. And the VC dimension is just linear separators in the plane, dimension 2. We show that this is 3. So there's no way to distinguish between them. In order to distinguish between them, we need to go back to this notion of margin that we discussed before, and I'm illustrating it here. So basically, we look at the extreme points, and we see how far they are from the linear separators. More formally, we've already seen that the margin gamma I of a point xi relative to this linear classifier sine of wx plus b is defined as the distance of xi from the linear hyperplane, which is written here, right? So it's basically the size of wxi plus b with normalized w, right? That's the distance. You've done a problem set on this, you computed it. If I have a set of points, the margin of the set of points is the minimal margin. So I'm doing minimum over all i's. So now the key point comes in. So now I'm going to say, you know what, I'm going to define a new hypothesis class, not the set of all linear separators, but once you've given me this data set, I'm going to split the space of all linear separators that you could use in the following way. I'm going to split them by the margin gamma. So I'm going to define H gamma to be the space of all linear classifier that separate this specific collection of data with margin at least gamma. Now, this is a well-defined set of functions. So the combinatorial parameter that we defined last time, which we call VC dimension, applies here too, right? So basically all we said is for every set of function, there exists a number that we call the VC of this set of functions. So H gamma also has a VC, and the nice thing is that the VC of this set of functions is the minimum between R squared over gamma squared and N plus 1. Now, basically, we know that if you are working in an n-dimensional space, the space of linear separators has VC dimension of n plus 1. We did it for dimension 2, the plane, and we showed that it's 3. It's true in general, it's n plus 1. So this n here just guarantees that we won't have disasters. So really, think about it with R squared over gamma squared. And as I pointed out last time, you've seen this before, right? This was mistake bound of perceptron, right? So, which is really good, right? Because it means that, you know, what we've done then, which we derived from completely different principles, and in fact was derived in the 50s, as I said, is also the right thing here. So it gives closure. Basically, plugging this into the generalization bound, we see that the gap between the error that we care about and the error that we observe on our training data depends on this R squared plus gamma squared, which is good. What does that mean? That basically means that if we consider this H gamma, we know that if we have a large margin, then we have a small VC dimension, which basically says if we go to this H1 and H2 options, it gives us the reason why we want to separate this data. Even though we have many, many options to separate the data, we want to separate it with this linear separator that has large margin, because it's going to give us better generalization. Now, you had this intuition before. Basically, if you put it in the middle and there's some gaps in the sides, new data examples that will come in have room to be there without incurring any noise, or without your hypothesis incurring any noise on them. So that's kind of the hand-wavy intuition, but now we have a firm mathematical ideas modulo your belief that this is really the VC dimension of this class, which I didn't prove, that this is the right thing. So, so that gives, I think it gives good explanation for what's happening here. In order to get from here to an algorithmic intuition, there's one other step, And this step is that the goal would be to find a separating hyperplane that maximizes the margin. And it turns out that if you have a bunch of options for W's, the one that maximizes the margin is the one that has small size. And this is something that we're going to prove next week. And it leads to an algorithm. Basically, from among all the W's that agree with the data, choose the one that minimizes the size. If you do this, it will maximize the margin. If this happens, you'll generalize better. OK? So the logical story here is clear. And we covered half of it. And next week, we'll cover the next part. OK, so why do I tell you all this? This is basically the summary of what we've done on learning theory. And we talked about a lot of things, in particular about guiding model selection, which is what we've done now, right? We basically said, among all possible models that you could have chosen, this theory guides you which one are going to do better. And in practice, it turns out that this theory actually led to a lot of good things. So we talked a little bit about the theoretical questions that led to Winnow. Next week, we'll talk about support vector machines, which I kind of motivated a little bit now. And next, today we're going to talk about boosting, which is another algorithmic framework that is very, very important, that was motivated completely by PEC learning, as you'll see in a second. OK, so that was the end of last time. As I'm moving to today, any questions? No questions. OK, so let me just, a few reminders. Projects are due tonight. Please send me email with this subject line. I'm not going to see any emails that arrive without this subject line on this topic, because I'm expecting, 80 or so. So please use this. Two other announcements. So in 2 weeks from today, we have a midterm. The midterm is going to cover everything that we're doing until today, not what we're doing next week. In class, here, closed books. Just, bring yourself and what you know. Pencils, that's it. So next week, I'm not going to be here, so Kai-Wei Chang, your head TA over there, is going to first give a review on everything that we've done this semester until today. And this is Tuesday, and on Thursday he's going to teach SVMs. So hopefully you come and you ask a lot of questions. Questions? Yeah.
Will there be a
So that's actually a very good question. What's the answer to this? It's already there. It's been there for weeks. So you guys should look at the website, because there's a lot of good things on the website. And there's several exams with solutions. And we also put notes from time to time. So yeah, so there will be exams. OK, so I want to say something about exams, because I heard rumors that people have heard rumors that the exams sometimes were difficult. So one thing I want to say that will be news to you, it's actually better for you that the exams are difficult. You may not think so when you leave the exam room, but really if you think a little bit deeper about it, it's better for you. So it's really bad that exams, or that your grade in an exam is judged by kind of stupid mistakes. You forgot to multiply by 2 here, or you forgot a sign here, and so on. you want to be penalized, if at all, because you didn't know something or you did something wrong, not because of kind of syntactic errors. And if the exam is too easy, what it boils down to, you know, the differences between people are really things that are unimportant. What we're trying to do, really, this is my philosophy for exam, is I want to be able to spread the grades so that the differences really reflect understanding, or at least understanding as it's reflected in what you've done in the exam. So, so we are trying to make it fair so that it really questions and sort of verifies that you know what we've learned here, but also some of the questions are going to be easy, some of the questions are going to be sort of in the middle range, that everyone that has been here and studied and did the homework and thought about it would be able to get, and maybe a little bit is going to be on the harder side, so that just people that really understand will get the final things, the kind of the last 10% or so. So we're doing it on purpose. I don't see any point in giving an exam that everyone can get 100 on, for the reasons I just explained. And I think it's good for you. So that's the philosophy. So there are going to be probably 4 questions with the hope that you can finish it in 70 minutes with minimal calculations. That's it. Any other questions? Yeah. Final is going to be cumulative, yeah. This one is about what we've done until today. In principle, yeah. In principle, it's cumulative, yeah. Yeah. Yes, okay. Excellent. Thanks for reminding me. So we already gave you problem set 4, and it's due next week on Friday night. It's much shorter than the others. There are only 3 questions. There's no programming. You know, it requires some understanding, but it's really just, you know, a couple of hours of work. No extensions. So the 96 hours policy does not apply as we've written there with red font for these problems. And then the reason is exactly that. I want to be able to put out the solutions for homework 4 so that you'll have them next weekend, which is the weekend before the exam. If I give 96 hours, we can do that. So please remember, tell your friends that are too busy that there's no extensions this time. We basically stop it. I think we let it go until Saturday morning, right? Cairo, is it Saturday morning? Okay, so if you really have nothing to do Friday night, finish it by Saturday morning, and then we're going to block it. So yeah, thanks for reminding me. And all the other solutions will be available on time. The grades will be available for 2 and hopefully 3, but definitely the solutions and the lecture, sort of the grading notes will be available. Other questions? Okay, yeah, another question. How about? I will be here and will learn something. If you still have questions, you can ask there. Yeah. So. Yeah. How many formulas are there? So don't remember the 13 in the numerator. If you write 11, in case I ask you about it, it's as good. But definitely you need to know the functional forms of this, because this is the heart of learning. So, you know, there was one formula there that has a lot of constants. I don't care about the constants, if that answers the question. But you definitely want to know that the relation between true error and training error and what's in the other side. Yeah. Right. Yeah, so I kind of talked about it without the numbers, and talked about, you know, the spreading of grades. Everyone called, I think, should be able, because you're listening and you're understanding what's happening, should get now, you know, 50, 60% of the exam, I think. If you really understand what's happening, you should be able to easily get 80% of the exam. If you really, really understand what's happening, you should get 100. That's the philosophy. And hopefully between now and 2 weeks from now, you will really, really understand. So, not a problem. Yeah, okay, so thanks. So everything is curved. I talked about the beginning of the semester. So if we missed something, and one of the problems was much harder than we thought, everything is going to be curved. So my assumption is that in a class of 100, more than 100 people, we actually know what the grade distribution is. I've seen it over the last 10 years. It's the same grade distribution. So, you know, we believe in machine learning, right? So so we're going to fit this curve. And in fact, we're going to fit two curves, one for undergrads and one for grads. And I can talk to you why I do it this way, but I think this is the right thing to do. So as I said, if there is, by mistake, a problem that no one can answer, it doesn't mean that you're starting from 75 and that this is going to be your grade. Everything is going to be curved. So now that you're all calm, Brian has another question.
So to summarize my understanding.
Yeah, summarize.
Work hard and...
Okay, you got it. Okay. So let's move to boosting. We'll boost what we just said. Okay, so boosting is a very important algorithm, or in fact, we can say that it's a family of algorithm or a learning paradigm that today is viewed as a way to put together a lot of possibly infinite even weak learners. So the original boosting algorithm was proposed as an answer to a theoretical questions in PEC learning that we'll get you in a second, in a paper by Rob Shapiri from '89. It's been a long time, but it's a really, really good paper, and that I recommend looking at, partly because it not only solved the theoretical problem, it actually provides a lot of insights to other things that are important in learning. For example, the relation between PEC learnability and compression. It has a couple of claims there at the end of the paper that are really interesting. I'm not going to try to explain them, but you can try to read it and understand. But really the key contribution, it turns out, after 20-some years of boosting has been practical. It's really a way to compose a good learner from many not so good learners. And really it's a family, it's a member in a family of ensemble learning algorithms, but it has the best theoretical guarantees and theoretical understanding of these members. So you can go to your Freund's webpage here and play with a demo if you want. There are probably a few other demos on the web, but I'm going to today I'm going to spend some time both showing an example that I think will illustrate what's happening there and give some of the theory. The theory is so simple, or at least the part of the theory that I'm going to show is so simple that it's worthwhile understanding because it gives some insight into a lot of the kind of key components or the definition of the key components in learning. Okay, so here is a motivating example. So, which was, by the way, one of the key, or the first, in fact, application of boosting. It was a system by AT&T that is called How May I Help You? Nowadays, there are quite a few systems that are trying to do similar things. The idea is that you call on the phone to AT&T, and you want to ask a question, and they want to automatically send you to the right person, someone that can actually answer your question. So you want to categorize automatically the type of call and then send you to the right person. So, here are some sentences. You know, I'd like to place a collect call. I'd like to do this. I'd like to do this. And the observation is that it's very easy to find some rule of thumbs that are pretty good, but not all the time. Right? So they're pretty precise, but their coverage is kind of weak. Right? So if you see card, if you identify the word card, then predict calling card. It's hard, on the other hand, to find a single highly accurate prediction rule. And that's the motivation for boosting. So boosting suggests to address this problem in the following way. Select a small subset of examples. Derive a rough rule of thumb that does well on this small number of examples. Put it aside. Get another second set of examples. Derive another rule of thumb. Do this many times. At the end, combine the rule of thumbs that you've learned into one single hypothesis. That's basically what boosting is doing. Now, of course, this is a significant simplification of what's happening. We need to figure out how to choose this subset of examples. Just choosing it randomly may not work. And then we have to choose how to combine all these rules into one single prediction rule, and we want to do this too in a way that actually we can justify. So boosting really is a general method for doing this, converting this rough rule of thumbs into a highly accurate prediction rules, and it comes with a lot of nice guarantees. Okay, so this is the theoretical motivation. So this is a definition that we've seen. Right, so this is pack learning, or here I'm calling it strong pack learning. For any distribution, for every epsilon delta of your choice, given polynomially many random examples, a strong pack learning algorithm finds a hypothesis that has error less than epsilon with confidence at least 1 over delta. Okay? Now, you could ask the following question. Let's define weak pack learnability. The same, but only with epsilon that is bounded away from a half. Okay, so I want to be able to learn, but my algorithm guarantees only that it's going to be better than a chance. Bounded away from a chance, that's important. Not sort of converging to a half, but rather bounded away with some positive number gamma here. And the question that was asked by Valiant that started this pack learning and Michael Kearns, part of his PhD thesis was, does weak learnability imply strong learnability? So let's assume I have an algorithm, and I know how to show that it's a weak learning algorithm. That is, for any distribution, for any epsilon delta that you give me, for any delta that you give me, what I can do is I can always find a hypothesis that has error less than epsilon for epsilon that is a little bit bounded away from a half, right? For accuracy that is better than a half. Does that mean that I can then boost the algorithm and do it for any epsilon. So I'm better than a chance. Can I be better than 99%? And so that was a question that a few smart people tried to solve. And in fact, in Mike Kern's thesis, the interesting anecdote is that he gave evidence that the answer is no. The way he gave the evidence is he showed that if, instead of for any distribution, you have a weak PEC learning algorithm on the uniform distribution, you cannot boost it to a strong PEC learning. Now, you shouldn't be surprised by that, because we already highlighted the fact that PEC learning over a fixed distribution is not such a strong notion as PEC learning over any distribution, right? We showed it by mapping or transforming our feature space in such a way that the distribution changes. It always changes when you blow up the feature space. And that showed that the for all distribution quantifier here is actually important. It's not just because we wanted to put there. And so, but anyhow, that's what he showed, and that gave some people the idea that maybe it's not going to work because it's not working over this fixed distribution. It turns out that actually the answer is yes. So Rob Shapiri proved in '89, he gave a first provable boosting algorithm in this paper that I pointed out before. Basically what this paper does, it calls a weak learner 3 times on 3 distribution, modified distribution in a careful way. And he shows that you can get a slight boost in accuracy, and then you can apply this recursively to boost the epsilon from bounded away from a half to any epsilon that you want. A year later, Yoav Freund gave a different boosting algorithm that was called boosting by majority. And this algorithm was actually started to be used in applications. So the AT&T team tried to do some experiments and ran it on a few interesting cases, but it was really limited in terms of its application because of various practical issues. In '95, Freund and Shapiro together introduced an algorithm that is called AdaBoost for adapted boosting, or adaptive boosting, that had a lot of practical advantages over previous boosting algorithm, particularly because it didn't have to know anything about the constants. It just adapted to whatever the data gave you under the assumption that you still have weak learning. And in fact, this was a revolution because after this, it's almost 20 years now, it was followed by a huge number of both theoretical papers that try to study it from different perspectives and understand why it works, and with a huge number of papers with practical applications. So it's being used a lot today in a lot of communities. And as I said, if you really don't know a lot about your domains, and you need a generic, very good learning algorithms, probably boosted decision trees with small decision trees is going to be your best general purpose learning algorithm, because it's give you expressivity because of the decision stumps plus the power of boosting. So this is actually, I want to spend a minute here because there's actually a very, very important lesson here for PhD students. In fact, 2 lessons on this slide. One lesson is this. So even though the problem was solved by Rob Shapiri, he solved the problem that Valiant posed, is weak learnability equivalent to strong learnability? Yoav actually worked on it for his PhD thesis, solved it in a completely different way that later on gave rise to AdaBoost. So the fact that someone told you that they solved the problem doesn't mean problem solved, let's not work on it. Sometimes a different solution that has some nice properties is worthwhile. So that's one lesson. Second lesson is this AdaBoost paper. So the AdaBoost paper was published in a rather esoteric conference called COLT, I think, because it didn't get in to better conferences. And the reason it didn't get into better conferences was that people said, well, we've seen this before. You know, there is an algorithm, it's called boosting. What you're doing is uninteresting. You're not adding something significant over what we already know. And it turned out that actually it was very, very significant over what was known, but the 3 reviewers didn't realize that. So it took, you know, a little bit stamina on the part of the authors to kind of try to push it and explain that this is actually different and important, and history is with them. So this is another lesson for you guys, that if you really believe that you're doing something good, the fact that it was rejected from conference A or B doesn't necessarily mean that you should be disappointed and move to doing something else. Okay, so now that we're done with that, we can understand what's boosting. Questions so far? Okay, so what is boosting? So I want to start to formalize it and understand what we're doing. So here is what we have. We have a training set, M examples. Yi is plus or minus 1. And here's what we're going to do. We're going to run T rounds. In each round, we're going to construct a distribution over the data set. We're going to denote it dt. We're going to find a weak hypothesis that we're going to denote ht. And this weak hypothesis is going to have error epsilon t on this distribution. Now, remember that in order to define an error, I need a distribution underlying these examples, right? Otherwise, error isn't defined. This is how we define an error. It's the probability that h of xi is different than yi, and I'm doing it under this probability distribution. Okay, that's important. That's the definition of error. Once I have this, and I've done this t times, we're going to output a final hypothesis. That's the algorithm. Now, of course, I need to give you a few more details on the algorithms. And the key detail that I need to give you, in fact, is how do I define this distribution? Because once I know how to define the distribution, I know how to compute the error of the hypothesis. So let's talk about constructing this distribution. So it's a distribution over my M examples. I have a fixed set of examples. So I'm going to start with a uniform distribution of the examples, right? Each example weighs 1 over m. And then, in the tth round, once I already have h of t, I'm going to define my dt plus 1, the distribution for the round t plus 1. And we're going to define it in the following way. So I'm going to take the existing distribution, dt. I'm going to divide it by something that is just a normalization constant. We'll get to it in a second. And then if I predicted correctly, okay, I see that I have some, this should be subscript here. If yi was predicted correctly, I'm going to multiply the weight of I under the tth distribution by e to the minus alpha t. If I made a mistake, I'm going to multiply it by e to the plus alpha t. Okay? We don't know yet what's alpha, but the form is clear. So now I'm just writing these 2 lines in one line here. So basically, it's the previous distribution divided by some normalizing factor times e to the minus alpha I, yi, ht of xi. Now notice that it's the same thing, right? What is the product yi, ht of xi? If I made a mistake, what is this product? Minus 1. And therefore I get plus alpha t. If I did not make a mistake, then this is positive, so I get minus alpha t. So basically, this is just a rewriting of these two lines. Okay. As I said, zt is a normalization constant, and alpha t is defined this way. We'll see in a second why do we want to define it this way. So it's defined as natural log of 1 minus epsilon t divided by epsilon t times a half. And then once I do this, the only other thing I have to tell you is how to combine the final hypothesis, and we're going to do it as the sign of the linear sum over all t, alpha t h t of x. Okay? So now let's see why does it make sense to do it this way. Yeah? What is? Zt is a normalization factor. We're going to define it later. But basically, it's normalizing it. So what I want is that dt plus 1 is sums. If I sum dt plus 1 or dt of I over all i's, I get 1. Right? So I start with d1 of I. If I sum it over all I get 1. You see? And I want to make sure that as I iteratively define dt of I always get 1. So when I define it, given the previous round, I divide by something to make sure that the sum over all i's is still 1. This is the role of z. Okay, so first of all, what do you know about this alpha t? Look at it a little bit. This is something that is related to the error that the hypothesis has on the current, the hypothesis HT has on the current distribution. What do I know about epsilon t in boosting? It's less than 1/2, right? Because I have a weak pack learning algorithm, right? So my error is less than 1/2. Otherwise, it would be uninteresting. So that's the assumption. We're going to make the assumption later. Here, this is just an algorithm. Doesn't need any assumption. But eventually, we're going to run this algorithm when we assume that epsilon t is less than 1/2. Epsilon is the error that we're making. We're going to assume that we have a way to learn hypotheses that make error less than 1/2. Okay? Yeah? So epsilon is not 1/2. Epsilon is less than 1/2. Yeah, bounded away from 1/2. If epsilon is 1/2, we can throw this hypothesis away because it's just random. Right? We have two options, plus or minus 1. So what happens if epsilon is less than 1/2 here? 1 minus epsilon then is greater than 1/2. Epsilon is less than 1/2. This ratio is greater than 1. Alpha t is positive. Agree? Under the weak learnability assumption, alpha t is positive. That's key. Why is this key? First of all, it says, okay, because alpha t is positive, what you do here, when you did not make a mistake, you reduce the weight on the example I, right? Because e to the minus alpha t is smaller than 1. On the other hand, when you made a mistake, you increase the weight of this example, right? So we started with a uniform distribution. We looked at the examples and what the hypothesis says on these examples, and we say, if we made a mistake on them, we're going to make them heavier. If we got them right, we're going to make them lighter. Right? So basically, the next round, we kind of focus more on those examples which we did not get right before. That's what it says, right? So the examples that we predicted correctly are demoted, others are promoted. Now, it's a different demotion and promotion than before. It basically says they become more important or they become less important, right? So that's one thing it's doing. The other thing it's doing, look here. Basically, what it says that in my final hypothesis, I'm going to give you a weighted sum of those hypotheses that I've learned on the way. Now, those hypotheses that had small error will have high alphas, right? If epsilon is very, very small, alpha is going to be large. So those hypotheses that have small error are going to be weighted heavier than those hypotheses that had high error, right? So these are the two things two observations that we're making here. Okay. Another thing that will be good later on when we do the analysis is to notice that what we do here is we recursively multiply the initial hypothesis by e to the something, right? Every round I multiply it again by e to the something. In the first round I multiply it by e to the alpha 1 something, and with h1, and then times alpha 2, h2, and so on. So think about what's going to happen when I want to unwrap all this product all the way back to 1 over m. I'm going to have e to some power, e to some power, e to some power, which will going to be e to the sum of all these powers, right? We're going to see this in a second. Okay, so let's start with an example, now that we understand the algorithm. Here are my examples. I have 10 examples. I think half of them are positive, half of them are negative. And I'm going to come up with some rule of thumb. My rule of thumbs, my weak, the class of weak hypotheses that I'm going to use are going to just be vertical and horizontal lines. So here is my first hypothesis, this H1. And H1 says that to the left of it, it predicts positive, to the right of it, it predicts negative. So I made 3 mistakes. I made 3 mistakes, which means, hopefully you can see this green, 3 mistakes over the uniform distribution. My epsilon 1 is 0.3, 3 out of 10. And if you do the math, you'll see that alpha 1 comes to be 0.42. Okay, now what do I do? Once I have H1 and I have D1, uniform distribution, I can define another distribution. What do? I take these 3 examples on which I made mistakes, and I change the weight. They're going to be heavier now, which I indicate here by making them larger. And all the other 7 points become smaller. I don't care whether it's positive or negative, they just become smaller. The sum is still going to be 1, because I normalized it. Next, I have this data. I had this as my H1. Now I have H2. H2 is going to be a vertical line here. To the right, again, it's negative. To the left, it's positive. Now I have these as mistakes. What's the key observation that you're making here? I made 3 mistakes, just like before. What is my epsilon? Make sense? Why is it that 3 examples out of 10 give me 0.21 as epsilon? These examples have lighter weight than these examples, for example. Each example weighs less than 0.1 now. Okay? So I got less than the previous epsilon, even though the number is the same, right? So remember, I don't care about the number, I care about the distribution that I have. And if you do the math, you'll get that alpha is now 0.65. And again, this makes sense. Smaller epsilon than before, larger alpha than before. Okay? Okay, so now I have this. And again, I'm computing D3, the new distribution. And now you will see that I'm taking these examples and I'm making them larger. I'm making these examples, making them smaller. And the rest, basically, I don't touch. Right? Altogether, I make them, well, in fact, I do make them, these become, again, smaller because I got them right. These become even smaller. So now I have kind of 3 or 4 classes of examples in terms of the weights that I have. Okay. That was H1, H2. Now I have H3. Horizontal line. Here, I'm predicting positive. Here I'm predicting negative. Again, I have 3 mistakes that are circled here. Again, the error goes down. For the same reason, because the weights of this example was smaller than before, and the alpha goes up. Altogether, I have this hypothesis. Now, I take the first hypothesis times 0.42, the second times 0.65, the third times this, and I got this concept. And magically, this concept actually classifies correctly all 10 examples. Okay? So I took 3 weak hypotheses, and I made them together one strong hypothesis. Oh, yes?
Was there any reason mathematically?
So if I reverse them, maybe I could have. So I didn't tell you what is my algorithm to find the weak hypothesis. But it could be that your algorithm will find the third first. And if it also makes 3 mistakes on the same examples, the same thing is going to happen. If it makes mistakes on other examples, perhaps other things are going to happen because I don't know what is the current weight of the examples on which I made errors, right? So what dictates the epsilon and consequently the alpha is what is the weights of the examples on which I got things right and on which I got things wrong. So basically, you can think about it this way. So in some sense, it's very, very similar to what you've seen before, which is it's a linear classifier over hypothesis. But in another sense, you started with an infinite hypothesis space, right? As before, in most cases, we started with a fixed hypothesis space, x1 up to xn. Here, I started with vertical and horizontal things, and I would place them, well, of course, depending on my algorithm, but in principle, I could place them anywhere I want to minimize the error that this type of hypothesis can give me on this data. So basically, what I've done in the first case, I try to run all vertical lines and all horizontal lines until I found something that minimizes the error. What do I have as a guarantee for boosting to work? That there exists a way, there exists either a vertical or a horizontal here that has error bounded away from a half, smaller than a half. Otherwise, this is not going to work. So, yeah?
Doing the error computation in this way,
Say it again.
since like in the second.
Right.
Is it just when you're computing the
It's this. So,
okay.
the sum over all i's weighted by the probability of the example I under the current distribution D of those examples on which I made a mistake. Okay? So if it was uniform, it would be just the number of mistakes divided by m. Here, it's the sum or the number of examples on which I made a mistake, but where each example is weighted by its current weight under the distribution dt. And that's really the key notion that you have to understand here, and that's why I'm going to do the theoretical analysis. I want to make two other points. One is that it's really interesting about boosting that it could be the case that say you've run it for 3 rounds, as we've done here. I already, had I wanted to stop here and get my linear sum, I already make no mistakes on these 10 examples. However, I can continue. No one said I cannot continue. Go to t equal 4, and in t equal 4, I will find another hypothesis. This hypothesis, H4, will make a mistake, because my language for hypothesis is just vertical and horizontal lines. There's no way to plug in a vertical and horizontal line for this data set that does not make a mistake. I will add another t, so even though my final hypothesis, my current final hypothesis makes no mistakes, another weak learner will make a mistake, and it's okay for me to keep going. And as we will see in a second, in fact, it's good for me to keep going, because my generalization error is going to go down. So it's kind of an interesting perspective on overfitting. So typically we say, what is overfitting? If you have small error on your training data, you want to be careful. Maybe you should stop learning, because at some point you overfit this training data and your error on the test data is going to grow. Here it's a different view. In fact, it's very difficult to get boosting to overfit. You really need to run it for many, many rounds. And this is, you can see here why, right? You can, even though you, on the training, you're not making mistakes after 3, you can still improving, and as we'll see in the second, in the bound, it's going to help. Yeah?
So here your combining rule is that add all.
That's how I do it, exactly. I take the hypothesis, the prediction of the hypothesis, times its corresponding alpha, linear sum. Yeah? So the only requirement I have is that I can always find a weak hypothesis. I don't care where from. In practice, you will have a class of hypotheses from where you're getting them, right? But in theory, there's no restriction on what is the set of weak hypotheses. It's only that at any point in time, when you're looking for a weak hypothesis, there exists one. And this is, notice this is a very, very strong assumption, because it basically says for any probability distribution, right? You notice that what has happened here? I mean, I change the probability distribution all the time. And now I got to a probability distribution that has these examples are really unimportant. They weigh very little. These examples are important, and these examples are important. This is probably not important also. So any distribution that I put on the data, it could be that at some point all my weight is going to be on one example, right? Which means that the existence of a weak learner now means I have a hypothesis that will get this example right, right? It's a strong assumption. In practice, you could argue, well, probably never holds. But maybe almost always almost holds. And it turns out that this is sufficient, because in practice, it's a very, very strong algorithm. Yeah? No. So don't mix linear algebra here. At least I don't know that this would give me a good explanation. Maybe it does, but this is much simpler, at least the way I presented it here. I don't know what is a complete set here. All I want is I want that for any distribution that I get to, there exists a hypothesis that is doing better than chance on this distribution. And let's get to the analysis, and then we'll see that this is good enough. And maybe there are, in fact, I'm sure that there are other explanations I'll show later. I mean, there's been many different explanations for why boosting works, but I'm going to give a very simple explanation. A one-slide proof, essentially, that I split over 3 slides, but it will hopefully give some ideas. Okay, so what do I want to show? I want to show that the following theorem holds. We run AdaBoost. We assume that epsilon t for all t is a half minus gamma t. Okay? That's my assumption. My error is bounded away from a half. But the nice thing is this gamma t, right? I don't need to know ahead of time what's gamma. Gamma could depend on t. Then the training error is bounded away by something. And we'll get to understand this something. The important thing is this. It's bounded away by e to the power of sum over all t of gamma t squared. What does that mean? Let's just simplify it even more, even though we can understand it here. Let's assume that for all t there exists some gamma greater than 0 but smaller than all the gamma t's, which I can always do, right? T is 1700. I can find gamma t between all the 1700 gamma t's and 0. Then the training error, I'm replacing all the gamma t's here by gamma, is less than e to the minus 2 gamma square capital T, right? So I replaced all of them by gamma. So when I sum them, all I have is capital T times gamma square. Okay? What does this mean? Training error is going to be as t grows, gamma is a fixed positive number, exponentially small as I want, right? Increase t, this is a fixed thing, it can be as small as I want. So my training error is as small as I want. Now, the first question that you can ask yourself is, why are you talking about training error? Who cares about training error? I care about true error, right? So that's the first question. And what's your answer? Because? Okay, but you know better than this. You're right. This is kind of the reason, but we proved last 2 weeks that that's enough. Because we have a hypothesis with small VC dimension, if you want, right? It's a linear sum. And therefore, if the training error is small, the true error is going to be small. So it's enough for us to discuss training error, right? So that's the cool thing of what we've done in the last couple of weeks. You now know that if you minimize the training error, it's going to be okay, unless you minimized it with a class of all functions, which we're not doing here, right? It's a limited expressivity class of functions. So that's one question. The second question we actually answered. What does this bound mean? It means that if we increase t more and more and more and more, we can get the training error to be as small as we want. And go back to the comment that I had before, that we can add more weak learners even though the strong learner, the combined learner doesn't make errors, it's still going to improve according to the bound. The training error goes down. Okay, so why is this working? So, okay, so first of all, we talked about this. Really what we're going to prove is this guy. We're going to prove that the training error is less than the product over all t's, 2 times square root of epsilon t1 minus epsilon t. Why are these two the same? It's just simple algebra, which I'm writing here. Epsilon t1 minus epsilon t, because epsilon t I'm denoting as a function of gamma t this way, it's a half minus gamma t, a half plus gamma t, which is a quarter minus gamma t squared. I didn't put the square root and the times 2, but you can do it. The second thing is I want to move from here, So this, I showed that this is this. Now from here to here, I'm using an inequality that we used twice already. 1 minus something is always less than e to the minus this something. And I'm using the something here as 2 gamma square. So basically, this is 1 minus 2 gamma all square. So I can replace this by e to the minus 2 gamma square. And then I'm doing product over all t's, which is going to change to e to the minus this. So basically, these two show that it's just simple algebra here. Yeah? I have a finite number of gamma t's, right? I stopped after 1,000 rounds. Each one of them had a gamma t. All of them were positive. Take the minimal gamma t over all 1,000 rounds, okay? Divide it by 2 and call this gamma.
Well, we don't know those gamma t's unless we run it.
But in the, I want to prove something, right? So I tell you, each round came with some gamma t. I don't know what it is, but I know that it's positive, right? So because I know that it's positive and I stopped after 1,000 rounds, there exists a gamma, and I just suggested how to come up with it, that is doing it, right? So I'm replacing all the gamma t's, but this gamma. Okay, so basically we showed now that we need to prove only this one. Okay, that's what I said, need to prove only the first inequality because the rest is. So let's see what we can do. So the first interesting step that we're doing is we unwrap the recursion. Remember, what was the definition of the distribution? In each round, we took the previous distribution and we multiplied it by e to the minus alpha t or e to the alpha t. So now that I open it, what do I get? The distribution, the weight of I in the final distribution is 1 over m, this was our first step, times e to the alpha t or minus alpha t or plus alpha t, which we've written as negative yi times alpha t times ht. I multiply all of them, and then because it's e to the product, or the product of e's to these powers, I can write it now as e to the sum over all t's alpha t ht. This was the numerator. The denominator is just the product of all the normalization factors that I had over time. I'm going to denote this by e to the minus yi and times f of I. This is going to be denoted by f of I. This is really my function according to which I'm predicting, right? I'm taking this linear sum of hypotheses, and the sign of it is my predictor. Okay? So that's first step. Okay, so now I want to prove the theorem. And the first step is going to prove that my training error is actually less than the product of all the normalization factors. Now, we didn't write down explicitly what is the normalization factor, but we can write it down. Before we do this, just notice that if I made a mistake with the final hypothesis, what's written here, it means that y times f of x is negative. It means that e to the minus y f of I is greater than 1. These are just tautologies. So now, let's see what is the training error. I'm claiming that the training error is 1 over m, sum over I, of either 1 or 0. 1 when I made a mistake, 0 when I didn't make a mistake. That's a definition of the training error, right? Now, I want to argue that this is less than 1 over m, I just copied it, e to the this. Why is this true? It's basically what I've written here, right? It's basically e to the minus y fx is greater than 1 when I make a mistake. Therefore, I'm replacing this 1 by something like this, it's only larger. Okay? Now I want to argue that step 1, which we did here, what is step 1? It's a definition of the distribution. So what is the definition of the distribution? This is equal to this, or write it in a different way, e to the minus yi f of xi is equal to m times distribution times this denominator, right? I'm just multiplying it to the other side, and that's why I got this. Right, this is just rewriting of step 1. And why is this true? Because the d final I over all i's sum to 1. It's a distribution. So this is a distribution over the m examples. So basically, very simple, I proved that the training error is bounded by the normalization factor. Now I want to show what is the normalization factor. And I'm going to argue that the normalization factor is this epsilon t 1 minus epsilon t square root. And again, you'll see that it's basically a little bit of algebra here. Zt, which is our normalization, by definition is this. Right? So what is the normalization factor? You have a distribution. You sum up over all the elements. The distribution before you normalized, that's the normalization factor. Because you want to divide by this so that the sum will be 1. So that's what I've written here. The normalization factor is sum over all i's, dt of I, e to the minus alpha I y ht. This is how we define the next step. So this is just a definition. Now I'm going to rewrite it, and the way I'm going to rewrite this sum is I'm going to split it to two sums. A sum over those on which I made a mistake, and a sum of which I did not make a mistake. Okay, so just splitting the sum. And again, directly by definition of the error, what is this? The sum over all i's of dt of I is exactly the definition of error. This is the question that you asked before. What is the definition of error? It's the sum of dt of I over all I on which I made a mistake. So I replace this by epsilon t. This is 1 minus this. It's the sum over those I did not make mistakes on. So it's 1 minus. And you can do a little bit of algebra, and you will get that this is this. Okay? So now step 2 and 3 together prove the theorem. You just substitute 2 and 3. So why did I do this? Basically, one of the key things that I wanted you to understand is the definition of epsilon t. And this proof forces you to understand this. So all this terminology that we used here is very simple, but very important for you to understand. Okay, so basically that's the key thing I wanted to talk about boosting. There are a few other methods that are similar to boosting in terms of, or functionally. I mean, they also collect a lot of learners and put them together in one way or another. And I'm going to mention it a little bit later. But basically, they're all doing similar things. Boosting, as we showed, actually has a nice proof that it's actually the right thing. And in practice, it's also turns out to be the right thing. So it works very well in practice. Final questions? Questions. Okay, so have a good weekend. Yeah.
Now we prove that with the capital